So our next speaker is Sujay Sanghavi. Sujay is a professor at UT Austin and also has an appointment at Amazon. Sujay is just generally a powerhouse in optimization, theory, algorithms, the whole thing. And so today he's going to be talking about catastrophic forgetting.
All right. Thanks to the organizers for inviting me. I always like coming to UCSD and I've come here many times. Today I'll be talking about mitigating catastrophic forgetting in the data-oblivious setting, and I'll tell you what that means. I also think I don't have the whole 45 minutes, so please ask me questions. I have the 45 minutes. I don't know if I can fill the 45 minutes, so please ask me questions. This is pretty recent work, and I'm very happy to get feedback. Right? Like, we are still running experiments and so on, to extend it, and I'd love your input. Okay. So these are my co-authors. There are people in my group. Ali is here, sitting out there. And then Sani, Hayden, and Rudrajit, and they're all students. Ali is a postdoc. Actually, Rudrajit is now in Google New York, in Wahab's group. Okay, so let's start with the so-called foundation model paradigm, which is pretty much the default paradigm nowadays. For any machine learning problem in at least vision and language, and often in other fields, right? Like every one of us has read papers and proposals, the foundation model for X, right? And so the foundation model paradigm is that you first train a large model on a lot of data in an unsupervised way, and it's typically like pretty expensive. Making a foundation model is a significant endeavor, right? And it's pretty hard to recreate, and often kind of infeasible to recreate, not just because of the level of compute, but also because we don't really know, what is the data mixture, what are the hyperparameters. We may or may not know many of these things, right? So it's kind of hard to recreate a foundation model from scratch, right? And especially if we focus on we do not have that training. We may have some proxies, but we don't actually have the actual, right? Okay, anyway, but so the foundation model paradigm is you take this big model and then you specialize this model for your specific, right? Your downstream task. Like maybe you wanted to be aware of the proper nouns in your own corpus. Maybe you wanted to answer questions that are only available in your own document, answers only available in your own documents, and so on. Right? So it's typically you pre-train and then you find. Okay, so I'd only seen these plots for I know some kids who do competitive swimming, and they make these plots for how good they are at freestyle, breaststroke, backstroke. And one is better than the other if one's pentagon or hexagon is bigger than the other person's hexagon, right? So people are now doing this for language models, and this is from which paper it's from doesn't really matter. It's a diffusion model paper, diffusion language paper. I mean, it does matter. The paper is a good paper, but the point I want to convey is that pre-trained models are pretty valuable, right? And they're broadly performant. Right? So, along many axes. So this is a pre-trained only model, right? I don't think it's been fine-tuned on a downstream data set, right? This is LADA, which is the largest kind of diffusion LM for language, So there are multiple axes. There's math, there's code, there's kind of a multilingual or Chinese data sets, and general tasks like doing. Right, and all models are kind of pretty performant on all these axes at the same time. So, we'll refer to this as general capability. It's not my terminology; it's terminology of the literature. Right. So, pre-trained models are valuable and they are generally capable. Right. What does this mean? This means that all of this performance is by the same frozen model. There is no specialization in this plot. Right, the same model has this performance on math and that performance on MMLU and so on. It's just the same model with either zero shot or few shot, where few shot means in context, but the model is not changing. just to further belabor the point, but with a less pretty picture, this was the main table in the JAMA paper where they had, when they released, I don't know if it was JAMA 1 or, but I think it was JAMA 2, actually JAMA 1 and JAMA 2, and they compared to a bunch of other models on many different tasks, right? And these are the usual ones like MMLU, GSM 8K, Vinogrand, HLSY. If you have been in the language model space, these are probably sound familiar. Right? And so the whole point of this is that we need this, like what people care about, or at least seem to care about, is that the same model is performant on all these things, right? And there's a pretty standard evaluation benchmark, right, which has these different things. Same thing for DeepSeek, except that it's like at an even larger scale. They still care, in the same way, right? But these are harder data sets, right? And these are like much bigger models. I think except for DeepSeek, everything is closed, right? Any questions? Okay, so we really, so I think the takeaway from the first few slides is we really care about general capability of big models, right? And from the little experience I have, with the chatbot style model at Amazon, it's also the case that once people interact with the general capability model, they expect that every chat model should be generally capable, right? Just like when we, interact with the search engine, we expect every search engine to be at the level of Google, right? So there's kind of a similar expectation, right? And the general capability is like a proxy for how good a human would perceive a model in general. Okay. So, what is forgetting? So, the question of forgetting is what happens to these models when they are fine? It's not a question I have asked. I'm not the first to ask this question, far from it, right? I will go over what people have done, right? But this is the question, right? It's like, what happens to these models when they're fine? Right? Which is, we are following the foundation model paradigm. We're taking some model, when we're using it, we're updating it for our use case, what happens? Right? So, they improve on the task or domain that they're fine-tuned on. Right? If you're reasonable in your fine-tuning, this will happen, right? But they degrade on everything else that they were originally measured on. Right? So, like if you're writing like the JAMA paper and you're working really hard to help this index of numbers be better than all the other indices of numbers, right? Anybody who fine-tunes JAMA is going to ruin that, right? So this is an example from a paper called MOFO. It's momentum filtered optimizer for, this is not my paper, okay? Right? Yeah, so, but I like this table because, it kind of conveys it in a way that we want to, and we kind of copied this style of table. It took these, it took Llama 2.7b, and they have several tables, but this is one of them. They took the Llama 2.7b, and they fine-tuned it on math QA, which is a math data set. And then they evaluated it on GSM 8K, which is a math evaluation, right? So you have the original model, it has some performance already on GSM 8K. Typically, it's not so great. I think that's why you choose GSM 8K, right? And if you do full fine-tuning of the Llama 2 on math QA, you get like a huge improvement in performance on GSM 8. Right? This is already well known, right? But when you do that, let's look at what happens to this full fine-tuned model on general capability, right? And so we see that there's a pretty significant drop in general capability, right? I mean, I'm not going to go back to the JAMA model again, but those differences were in the 1-2s, right? This is in the 5-8s, right? So it's a pretty significant drop in capability. And then these are other methods to like mitigate forgetting, and they show that all of them also have this drop in general capability. So my talk title had 2 parts: catastrophic forgetting and the data-oblivious setting. This previous thing, this is what I'm going to call catastrophic forgetting. We can argue whether it's catastrophic or not, but it's kind of forgetting, right? And then what is the data-oblivious setting? The data-oblivious setting is, I think, the setting we are all in, at least in academia, right? Where we don't pre-train the model, right? So we don't know how pre-training is done. Like literally all we have is maybe, the model itself, right? The weights, right? And so the question is, how do we mitigate forgetting when we only have access to the model and we don't have access to the original data? Because, so the reason we found it this way is because in, kind of maybe classical machine learning, if you have two things you care about, one is the performance on the, let's say, pre-training task, and the one on the downstream task, you would make a loss function that depends on both these things, and then you would trade it off, and then you would find some model that can do better on both. Right? This is not allowed anymore because we don't have the pre-training data.
You can use the model to compare the data, right?
Yeah. So this is a good idea. Let me come back to the second. Yes, that's not what we do. Okay. So this is the question. This is what I call the data-oblivious setting. We have downloaded Llama. We have no idea how to train, right? And before we want to fine-tune it so that we don't ruin it. Okay. So let's have some notation. So theta is the weights of the model, and for every sample I in the fine-tuning. So we only have the fine-tuning data, right? And so for every one of them, there's a loss function which is fi, which depends on theta. And let's say theta star are the weights of the pre-trained model, right? So we have the fi's and we have the theta star. So standard fine-tuning is, you try to minimize this empirical risk, starting from theta, right? And for our paper, the fi will be the standard fine-tuning loss, not the. We are not further pre-training; we are standard fine-tuning, right? Okay. Okay, so this is standard fine-tuning. Like you just want to minimize this, but you'll do it by some atom or something. So you start from initialization, which is the original one, which is the pre-training. Okay, so there's a bunch of approaches, and I'll go over them. I mean, obviously, you guys are not the first one to think of this problem, right? So the first one, is actually a pretty classic paper. This is probably the oldest paper in this. I think the oldest reference in this talk is from 2016 or 17. Which kind of says the obvious thing, which is you have an original theta star that you don't want to deviate far from, right? So just put in a regularizer that penalizes deviation from it. We'll call it L2 regularize. Okay, so I just call it L2 regularize because we will see that in our table in the future, in what comes up. And so penalize deviation from the pre-trained model during fine-tune. So instead fine-tune with this, starting from theta star. You always start from theta star. Nobody starts from random during okay, this is the MOFO paper. Yeah, so what they do is, don't fine tune everything, right? So just pick a subset of your parameters and fine tune only those. And then the question is, how do you pick your subset of parameters? So what they advocate is that you first pretend you're going to do atom, and you find the momentum for each parameter. You find the momentum term, and then you keep the parameters with the largest momentum term. Okay. So you only update those. Don't update all the parameters. They show that this works while doing the same thing with per feature gradient, per parameter gradients didn't work so well. Okay, and then they have some intuition about why that.
So in each iteration,
In each mini batch iteration,
they can update a different set of parameters.
they'll update a different set of parameters. Yeah, okay. So I shouldn't say do not fine tune. I said do not fine tune everything in every step, but select which ones you're fine tuning based on moment, as opposed to based on gradient. Yes.
So I'm assuming that works because you're not changing the ones that change the final result a lot, and that means that you're not affecting the model. I don't think I'm able to
Yeah, no. So okay, I think you got it right. So what they want to do is, they want to identify the parameters that have a big effect on the downstream task, and they'll update only those, right? And that's probably better than, yeah, and so they'll update only those. And, if you kind of begin with the assumption that for the pre-training task, all parameters are equally useful, then we have found some parameters which are really useful for the downstream task. Let's focus only on those instead of changing the other one. Right, so yeah, so this is my intuition for what they're trying to do as well, which is pick the parameters, first decide I'm only going to update 10% of the parameters, then pick only the parameters which are really helpful for the downstream task. The first thing you would think of is let's pick based on gradient. That doesn't work so well, so they pick based on momentum, and that works.
But you cannot really guarantee that you're not going very far from data star. You can go very far.
Yes, I mean, it depends on what is the fraction
Right.
of parameters that you update. Right, so, they have a threshold of, this is not my method by the way, but they have a threshold of how many parameters they want to update in every step. But you could go pretty far.
Can you regularize for what distribution you might generate?
Regularize for the distribution you generate.
Instead of the weights, like, data star versus K.
So get us out of the parameters, which are, yeah.
I'm saying, maybe for this sample, what distribution they would generate, you don't want to deviate from that.
Right, so that's a different one. Right, like this is sub-selecting weight. What you are saying is to change the loss function.
Change the loss.
Yeah, so yes. Yes, you can change the loss function. I don't know if any, yeah, we can, I can change, actually I change the loss. But not the way you say it, yeah.
I assume the updates is better would be like as sparse of subset, right?
The update will be sparse for in every iteration, but in the next iteration it will be different
Yeah,
sparse.
right. Defense of power trade.
Sorry?
So defense of power trade would be.
Yeah.
Other things like compared to that number utilization, that we had.
Actually, we have not, I don't know how MOPA works for me because we didn't implement. This is an ITR reject. It came out during our, I mean, it's a good paper, everybody. But it came out during the time that we were doing our own and we didn't have time to compare against them. But they compare. Okay, another approach is to do parameter efficient fine tuning, right? And so, I guess the title says it, LoRa learns less and forgets less. Okay, and the higher the rank of LoRa, the more it learns and the more it forgets. Okay, yeah. And so, if you want to think about it in terms of the notation, what we have now is that we're just updating a theta small, and our final parameters are theta small plus theta star. Right? Where theta small is like rank constrained. Every matrix is rank constrained like you have in LoRa. So your theta small starts from 100, and it's the only trainable parameter. Okay, here's approach 4, which is weight ensembling. Right? So the idea here is first just fine tune, starting from theta star like how you were before, right? But then you say that, but you call that theta 1, and then theta final is a convex combination of theta 1 and the original theta star. So it's literally like every matrix you just add, like alpha times the matrix that comes from theta star, and 1 minus alpha times the matrix comes from theta 1, and just add them together. Okay, it's called model swooping, model averaging. It sounds like a crazy idea to me, but it works in many different types, including this set.
It's doing this only at the end once.
Only at the end once. Yes, that's right. So you just first run a full several iterations of fine tuning, and then at the end you just have it. And you can change alpha and get some kind of Pareto curve for this, not true Pareto curve, but a Pareto curve for this method.
Okay, so you're not learning alpha here.
I don't think they learn alpha. They just show how. So there are two things, right? There's general capability and there's downstream performance, and how alpha trades off between them, and they show that it trades off. It trades off between them better than than the straight line joining the two endpoints alpha equals 0. That's what it is.
How taking convex combination, like these are transformers and.
Yeah, just every matrix, right? So first layer, attention head for the key, the attention matrix that maps the embedding to the key. From model 1, model 2, add it together.
But what is why would this even work?
I don't know. I'm not going to answer that. I actually do not know. If somebody knows, they can.
think the argument that I've heard from Livy is that if you think of these as convex models, then convex averaging is fine. Now, fine tuning doesn't change the parameters too much. Maybe you're already near, optimum. I mean, you can kind of wave your hands wildly and make this argument.
Yeah, this is it. I mean, this looks right.
Yeah.
Okay. Yeah.
Some kind of regularization with respect to the stuff.
Is this a regularization with respect to? Not really, because you're running this full optimization problem without any theta star. You're starting from theta star, obviously, but there's no regular. Yeah. Not sure. Yeah. Okay, so approach 5 is ours. Okay, so there are no other approaches which change the loss function. We change the loss function, but there may be other ways to change the loss function. I think you're thinking of something different. But anyway, yeah, so we have an approach which we have another approach, okay, and it's kind of it does what it does. It's better than the previous ones, and it's also complementary and additive to others. And so you can use it in conjunction with whatever else. Okay, so what's the idea? So the idea is sample weighting. Okay, so at a high level, what are all these things? What are all the approaches doing, right? They are trying to discourage big moves away from theta star. Right? You have the original model and you want to discourage big moves, or rather, even if you do move, it should be in something that helps the downstream task, but it's not as big as standard fine tuning. Right? So you can have like less parameters, or you can have LoRa, or you can have L2 regularization, and all of them are trying to discourage a big move, right, from what would have happened in vanilla fine tuning. Okay, so if you think of it, then each sample I causes a move from theta star of magnitude times its gradient, right, at the original point theta star. Right, and this gradient is something you can actually evaluate. So if I give you a fine tuning data set and I give you theta star, you can evaluate this gradient, right? So anyway, okay, so I'll just keep that in mind. So our idea is to just deprioritize samples which cause big moves. So, start from theta star, but solve a weighted loss function where the weights come, where you have a per sample weight. And we will choose this per sample weight on, based on theta star.
Based on the gradient, right?
No, but we would like to base it on the gradient, but we don't.
How we know?
Yeah. Okay, so this is the idea, right? That we just have a weighted loss function area per sample.
And these weights are fixed ones.
These weights are determined once and fixed.
So
Yeah.
in the worst case, let's say you have fine-tuned data set, but only one sample helps. That's the only sample that has non-zero magnitude. Everything else has
Right.
zero gradient.
Right.
But then in this worst scenario, you will sample that, filter that out. You're trying to fine-tune with usually sample. So I don't know.
Right.
I'm trying to understand this kind of common example or the worst case scenario versus the generic. I also see why this is useful, but you can be more about like how do people
Yeah, no. So I think it's pretty easy to construct worst cases for any of these methods, except maybe L2 regularize, which maybe not, right? But other than that, it's pretty easy to construct bad cases. Now, for us, we are still, I haven't told you how we are determining the per sample, but we are not going to end up only focusing on a few samples. We do not want to do that explicitly, right? So that might mitigate some of what you're saying. Okay, so this is the broad idea. We still need to figure out how to determine the per sample. Okay, so first, as pointed out, the obvious thing based on what I just said is, if you have a large gradient, of the model at theta star, you should give it a low weight, and you should give it a low sample. So yeah, I think we can do this. The reason we didn't actually do it is that calculating these gradients is memory and compute intensive. right? Because you need like a backward pass, which takes more memory than just a forward pass. But you can do it. Like if you're fine tuning data set is small, I think you can do it, and you can have a variant of our method, which depends on the data. Okay, so instead what we do is that we just base it on the loss, because the loss just needs a forward pass. And so, okay, like typically, both losses and gradients are computed in batches of samples, and how many samples, and you want as large a batch as you can fit into your GPU. And you can fit a smaller batch in GPU if you have to calculate, if you have to do backward passes on all of them, and a larger batch if you only have to do forward passes. This is already known. So okay, so that's why we base it on losses, but yeah, it's actually probably more principled to base it on the gradient. Yes.
You compare the two approaches on the small data set?
No, sorry, yeah, I mean, yeah, that's one of the things we are still doing, right? Which is to, like based on the magnitude of this.
So among the approaches, prior approaches that you mentioned, one of them was choosing the parameters according to the magnitude of the gradient and all the updating all of it.
Choosing the parameters, yes.
So have you said that as an approach, right? And we need to go to
No. Oh yeah, choosing the parameter based on the gradient of the parameter. So, like,
not at the first algorithm flow.
sorry, this is weighting the samples. And like,
Individual.
this is weighting individual samples, but it's updating all the parameters. But that was choosing the parameters to update. Right? So it's different. Yeah.
One more question. So if you look at the first one, let's say you choose pi t, like the inverse of the, let's say 1 over magnitude, it becomes more like normalized gradient descent. Let's say the vanilla gradient descent applied to that setup. So do you have any like relation like that for the second one as well?
Yeah. That's a good. It's not normalized gradient descent because it's based on the reference model feature,
yeah.
right? Like it's not based on. This is a one-time thing, right? Like we're going to go over the data set and make pi for everybody, and then not touch it.
But at the beginning of the fine tuning will behave like normalized gradient if you choose one over gradients.
Doesn't normalized gradient descent need to have this be the theta current as you are updating?
Yes.
So, but yeah, so
it will deviate from it, but initially.
maybe initially, right? Like maybe first few steps, you're right, it might be like that, but after that. Okay, so how do we determine pi? So, we need kind of two things, right? So first of all, we need what we just said, which is that, if the loss of sample I is bigger than the loss of sample j, then its weight should be smaller. And the distribution of pi should be spread out. Maybe kind of for the reason you mentioned, which is you don't want to focus and concentrate on a few samples, right? And both requirements can be met by in a pretty standard way by entropic regularization, right? Like you just add this little regularizer, which is tau times the entropy of pi, and that spreads pi. Okay, and how much you spread pi out depends on the tau that you choose, which you as a magic parameter. And so one way you can think of choosing pi is that for every sample, you have this fixed number, fi of theta star. And then you just minimize this function, right, which is then the weighted pre-trained loss that we're ultimately going to use, or like a proxy for it. We're going to use with the theta, which changes, plus this entropic regularization. Okay, so this is what we do. And we choose pi in this way. And so, if you solve it, it kind of turns out that the pi that solves it is this. This is a method, it's called flow. Okay, so what is flow? This is flow. So you take a pre-trained model and a data set for the new task and some temperature parameter tau. And then, fi of theta is I sample loss at theta. You first compute all the sample weights, then you have a weighted loss, and then you fine tune with the weighted loss. Right. So in our experiments, we chose tau to be the median pre-trained loss on the entire fine tuning case. Right. So we did one full forward pass, before we did any training, just to determine tau. But you could also have it just be the median of the mini batch that you load. Right. So you don't need to do this offline forward pass. What you can do is every time you load a mini batch, you just compute the loss on the mini batch, and then you have a tau which is the median estimate of the mini batch, or, and, so that's like, fully online tau, and then you can have something, you can make it be a running average of previous tau, whatever, right? Tau is supposed, like, I think the median is a good choice. But other than that, there's nothing, yeah, and so, and any proxy you can get of that in an online fashion, if you care about online, you can do that. Okay, so I just want to mention one thing, which, for people who might have seen it already, this is very, it looks very similar to this thing called a distribution robust optimization, which is a different problem, right? So what DRO solves is, it's a min-max problem, right? Where, you want to minimize a loss over theta, but you want to pay different attention to different samples with a goal being robustness. Right? Just robustness in training. This is not about like pre-training, fine-tuning or anything. This is just like standard ERM model training, but if you want to do it in distributionally robust way, then this is the DRO objective. And it looks very much like our objective, except that it's, kind of the exact opposite, right? So the weights you get from DRO will be this. Right, like for any theta, okay, so if you solve DRO, you have a theta, you make the weights, then you update theta, then you make the weights. And so at every point, so it's a little bit different from ours. Ours is one shot, right? But the weights at every time will be e raised to plus, and well, we are e raised to minus. Okay, and so I think what that means is, also we haven't run experiments to see this, but if you fine tune with some kind of DRO objective, it will actually accentuate forget. This is what I think. Okay. When we are running experiments, we'll see if it's true or not. Okay. So let me get to our results and then maybe some theory as well. So then, all right. Yeah. So our experiment setup is pretty similar to some of the papers we compare against. So we have two pre-trained models. Gemma 2.2b and Llama 3.2 3b. And our downstream task is to fine tune on MetaMath QA, which is one of these like data sets that help math performance and evaluate on GSM 8K, just like we saw in the MOFO paper. And then for general capability, for a proxy for that, we use Common Sense, MMLU, and MVP. And there's a pretty standard like evaluation harness which we use for the evaluation. This was a setup in both LoRa learns less and forgets less and remote. Okay, so these are our results, right? So these are the different methods. So the standard fine tuning, YSFT is model averaging, LoRa is LoRa, and then L2 regularization, and then ours. We haven't compared against MOFO, as I said, but it's on the cards. Yeah, so we see that we are. As a standalone method, we are comparable / slightly better. So, okay, what average is we first take the average of these three, and then take the average of that, general capability performance with the target performance, and that gives us this. So it's kind of like on the Pareto curve between general capability and target performance, it's like the 45-degree line. That's average. But these are the individual numbers, for them. And I mean, the differences are somewhat slight, but that's the case in LLMs. Like many differences are pretty slight. Yes.
So what you are doing in your algorithm is that you're analyzing the KL divergence with respect to the weight.
With respect to the
pi weights of the sound, right? Now, separate, work in fine tuning, mostly for safety fine tuning, where they have some safety objective, but they also have an analyzer which for the KL divergence with respect to the original language model, right? So you as pi of y given x. This is like a probabilistic model, so you also analyzing the divergence.
So, but that is KL divergence between logics.
Between, yes, Y given X.
Between logics.
Yes, probably not.
This is not logic. Right?
Sure,
Yeah.
sure, but it's a separate
Yeah.
line of work. But that's also used for time. It might be worked through with your content.
Okay. Yeah.
Because that's also there.
Yeah, I think doing something in logic space, I think that may be also what he was saying, is definitely, there is definitely a good direction we haven't pursued. And also, I haven't seen any good papers thinking about forgetting in the logic space.
Yes, they're doing it for safety alignment.
Safety. Okay, yeah, so I mean, I think these results show that, at least on the 45-degree line, we are better, right? But not, of course, for every data set, right? I think what I find more interesting is that it is actually additive, right? So, L2 and LoRa were two of the methods that we talked about. And then, L2 plus and LoRa plus is, we just do L2, but, we also put in our sample rate. And so A1, A2, A3 are just for, it has a common sense MMLU and BPP, and B1 is GSM 8K. And so it improves both of these methods. So, you can do it in addition. You don't have to take one of the other.
Is there a comparison of how extensive the all these different methods are? Because I can have a super method which does everything and then just takes the best.
Yeah, I think they're not very expensive,
You know,
right? I mean, it depends because of fine tuning, right? So depends on the fine tuning data.
Just to get a sense, how many examples are there usually for fine tuning?
I think we used a few million samples, which in the scale of these models is not good. The pre-trained data is in the multi-billions, but the Llama is still. All right, so this is for language model where you just update the full model. Fine. Okay. But there are many applications where you take the body of the model but put a task specific head. Right. So the simplest example is image classification, where it's pretty standard to take a large model trained on a large data set and then remove its prediction head if it has one and put your own prediction head and then use that as the model for your data set, right? So for example, you can take a model trained on ImageNet, which I've called the large set here, right? And then you can remove its prediction head, which has 1,000 outputs, just remove the head, and put a new prediction head, which has 100 outputs, and train the new one on C400, either by linear probing and then or full fine tuning. Right? So this is how people use pre-trained models when you have a task specific head. So so we can apply flow to this kind of situation as well. But it's pretty important to do this, which is that first you should make a linear probe prediction head. So the thing is that flow, as I just described, doesn't make any sense because the pre-trained model by itself doesn't have any loss, right? Because it doesn't have a prediction head, right? So if I take a model trained on ImageNet 1K and I say what is its loss on a C400 data set with its different labels, that's a nonsense question, right? So what I need to do is I need to make it a model which has some loss on on my actual fine tuning data set. And so what I do is you need to make a task specific head, linear probe it, which means freeze the body and only train the head. And now you have a pre-trained-ish model on your downstream data set, and then you can use that for the weight. Right? So do everything else the same.
Okay. So will it result our performance on ImageNet? That's what you want, right?
So after linear probing, right? So the body has remained the ImageNet body, but I have put the CFAR head. Now, if I want to evaluate its performance on ImageNet, I throw out that head and put the original ImageNet head, and that makes it the original ImageNet model. So we're all good.
That's step 3.
Yeah, once you have step 3, it ruins it. Right. So yeah, so in what I show, the performance on ImageNet, on task, I'll call it task A, which is the ImageNet performance, will be this ruined body with the original head. And there's no way to kind of save it because we don't have image. Like in our setting, we don't have image. Okay, so we take a bunch of small downstream tasks, and for each method, we take the pre-trained model is a ResNet, larger ResNet range on ImageNet 1K. They're pretty standard. Yeah, and so here, the improvements are like much more drastic, right? And it may be because of the effect of the per task head, right? Like when you take some body and you take, you put a new head on it, it really ruins the body, right? I think, right? And yeah, so, so this is the emergent 1K accuracy is the accuracy on the original data set. When you do linear probe, the body hasn't changed at all, so the performance remains the same. I think that's your question. But then once you start doing anything, it degrades pretty rapidly, right? And so here, like flow really outperforms all these other methods when you have task-specific parameters.
Did you train the head again after destroying the body or use your old head?
We cannot train the original head again. We don't have emergent one, right? I have made my problem, so we don't have this head. If you make, which I think is legit, I think, because like we are also doing this now with Clip, and Clip is trained on a huge data set. We don't have it. We have problems. Okay, yeah, and again, same thing here. We are additive with the model. So if you have some other method and if you add our thing to it, it improves. Okay. All right. So I imagine I didn't have much time for theory, and so I didn't put many slides. But we do analyze flow for the linear setting, right? And so in the linear setting, we have y is equal to theta star x, where being the data. So the theta star is like the ground truth, and the x has some distribution sigma in the pre-training data. So these two things are for pre-training, and then we have fine-tuning, which is sigma tilde and theta tilde. And we find the set of conditions on these four quantities so that flow is probably, under which flow is probably better than a model averaging, which, this is a convex setting. And so as Tarsu said, in the convex setting, model averaging, it has a reasonable basis, right? Yeah, so we find that, so we show when flow will be better than that. And we also show when it's better than L. Right? Because and we choose these two because they're actually, we can find some closed forms for compare. Okay. Okay, so I'll summarize since I think I'm out of time. I think, okay, selecting samples is a cheap and complementary way to mitigate catastrophic forgetting, right? And if you have task-specific types, I think it shows pretty good performance. And more generally, I think like solving catastrophic forgetting is like a good first step to continual learning. And it's a pretty well-defined problem where it's not, I don't think it's solved.
One question. There is also this setting where you are trying to operate the factual knowledge, because I think in your task you are evaluating, you're not testing the factual knowledge, right? So if you want to update some factual knowledge, but you want to preserve some factual knowledge. So sometimes what happens is you update some factual knowledge, even the other factual knowledge gets to
I have not thought about it, but okay, sorry. So is there a data set for this? If there's a data set, we can definitely try it. But I think it's very interesting. Like if you have a model trained on news updates, yeah. But actually, if there is a data set to evaluate, I would definitely want to try it. Okay.
Okay, thanks again.